we're coming back to first principles, all right? And actually, this is really good because you guys as 3-unit students can do this next part. And 2-unit students, well, you'll see why they struggle in a second. First principles, okay, says, for any given function, right, its derivative is given by, how does first principle start? Limit. As h approaches 0 of? Good. You've got rise on the top. All over h. Okay, good. So let's just take that and do it for sine. Okay, so the derivative of sine x is equal to limit h approaches 0 of, and right away you can see the problem, right? At least you can see the problem for 2-unit students. What's the problem? We're gonna have to do something with this guy, right? And trig expansions, that's what you guys do, right? So we're gonna expand that in a second so we can work with it. That's all over h. Okay? Okay, so remember what our goal is. It's to somehow avoid having an h on the denominator, or if there is an h on the denominator, to be able to deal with it in some way. Okay? So let's expand and see where it goes. Get that? Okay, you happy with that so far? Yeah.
How often is first principle tested?
In this exam, all the time. This is the exam that's all about introducing the idea of calculus and first principles, that kind of thing. After these exams, we start ditching first principles because you learn all the rules that no longer require them. So the reason why we're doing it now is because, this result, before you start using it, you want to actually prove it. And that's why we come back to first principles. Okay. All right, now, by the way, just as a side note, you probably don't think there's anything wrong with this line, but it's a bit weird because there's actually 2 things in here which are actually, they're names of functions. They're cosh and shine. Don't ask me why, that's just why people pronounce it that way. They're called hyperbolic cos and hyperbolic sine. Anyway. So, for us, it's just sine of the constant.
Isn't
Sin.
that
Okay.
Isn't that cos? No, sine to. No. Sine.
I've just done the expansion, yeah? From there to there. Okay, now,
Going back.
what do we do here? What can we do? In previous times, what we've done is to deal with this a little better. We've had a couple of tricks up our sleeve, right? Sometimes we added and subtracted something on the numerator to make factorizing easier. Sometimes we broke it apart into 2 different limits, okay? And that's what I'm going to suggest we're going to do here. Now, I admit, it's not going to look that intuitive, but just follow with me. Next line, let's go with this limit. And here's what we're going to put down. Make sure I write it correctly. I'm going to factorize first. Sound it? Yeah, good. Okay, now, at this point, why have I factorized? This cos h minus 1 is going to be really useful for us in a second, okay? But before I can use it, I need to split apart these 2 parts of the fraction into 2 different limits, okay? So, I'm going to put the first one here, which is sine x all over h, okay? And I've got another limit over here. Okay, now, do you remember, just as a side note, okay, that when we were evaluating limits, sometimes we could take things out of the limit if they had nothing to do with evaluating the limit. So example, okay, when I said take the limit as x approaches 2 of 5x, okay, because this number 5, right, it doesn't change no matter what value x takes, right? So I can write this as 5 times the limit as x approaches 2 of x. Okay? So not only can I think of it as, oh, it's going towards 10, I can think of it 5 times bigger than going towards 2, which is the same thing. Okay? And when you look at this line, I can do much the same, but it's not as obvious because it's all letters, right? What can you take out? from both limits, you can take out different things. Okay? From this limit, you've got this sine x, which has nothing to do with the h. And over here, you can take out cos x, which has also nothing to do with the h. Okay? So let's take those out and then see what we've got. Okay. Now, again, I want to pause for a minute. You've got two limits here, and they both have their own tricks associated with them. Okay. So let's have a think about this guy. Okay. The limit as h approaches 0 of all of this cos business. Okay. Now, what does cos look like? Cos looks like this. I'm going to draw both sides of it, actually. Okay. So what happens to cos of h as h approaches 0? And you can think about it from above and below. We were looking at this last lesson, right? What does cos h approach? 1, correct. Because as I'm getting towards 0, the value up here is just 1. Okay? So I'm just going to write down on the side here, because it's helpful to me. The limit as h approaches 0 of cos h, right? That limit is just equal to 1. Okay? Now, by similar logic, okay, let's think about this one over here. Now, this part's trickier. This result actually relates to these earlier steps. So if you're not satisfied with this, I'm going to prove it more rigorously later. But let's think about these graphs, okay? Sine of something, okay, and h. If I think of sine of x and x as two different functions, okay, that's what sine looks like, and x is just a straight line. Passes through the origin, okay? Now, you can go and verify this, number one, by looking at a computer, graph it, and zoom in, okay? Or just take some measurements. What's happening is you're approaching the origin. As you look at this one and look at this one, they're both approaching the same point, okay? But not only are they approaching the same point, if I zoom in, right, everything is getting really, really close together. Like these gradients are approaching the same thing as well, okay? So therefore, sine h over h, even though I can't just put in h equals 0, this limit, it's a really important one, so important that's why I'm going to prove it later. This is equal to 1 as well. Okay? So I'm going to take both of these limits, both of these facts, and I'm going to bring them in. Okay? Let me go back to my own proper color. What's happening here? Cos of h is going towards 1, right? So what's cos of h minus 1 going towards? Yeah, it's 1 minus 1. So this whole thing becomes 0, right? So if that's what the limit is, you know, this poor guy at the front, he's like, I thought that was significant. Well, actually, he gets multiplied by 0. So he just vanishes. Okay? Now what happens to this side? Okay? This limit, as we saw from the graphs, it approaches 1. So cos x times that limit, which is 1, is just cos x. The derivative of sine is cos. Okay? So, what do we require? Number one, this whole first principle setup. Number two, this trig expansion, okay, which allows us to factorize, break up the limits, and so on. And number three, the key piece, I'm just looking if we have any time. This limit here, that's the important one, okay? And you might think, okay, it's not that, it looks about right, okay? But this, you know, this looks about right is the same intuitive sort of approach which gives us the right result, but isn't enough to say I've proved it, okay? So,